Bism- Bismillah ar-Rahman ar-Rahim. We start today talking about the long short-term memory. It's a type of neural network that has come to solve the issue of vanishing gradient descent as we explain in the simple artificial neural network. Let's start by the forward step, then we will talk about the back forward step. Long short term memory, and it's an artificial neural network. Before we start, let's talk about the terms that we are going to use in this system of equations, which consists of 6 equations. C sub t is the cell state, which represents the long memory cell state. H T represents the hidden state for short memory, and it's non-linear transformation of the long memory into the output space, as we will explain now. H sub t is the hidden state. Ft represents the forget gate, and we will use it to make a selective memory mechanism, as we will explain now. Forget and the input gate will help us to decide how much from the new candidate data to insert into our system. This is input gate. Input gate. OT is the output gate. Output XT is the input at the time step number T, the current time step. Input at time step T. W is the learned matrices of weights. U represents the learned weights for the hidden state. X for the input, for the xt. Weights for inputs. U are the matrices for the weights for the hidden state. And B are the biases. And we will use them in almost most of these equations. Now let's start by the system of equations for this long short-term memory. We have said we have 6 equations: 1, 2, 3, 4, 5, and 6. Equation number 3 represents the candidate data. It's the new information that we feed into this artificial neural network at this time step number T. It is C tilde. We didn't write it here, but here it represents the candidate data. It's an equation. It's just linear transformation of the input data as well as the hidden state which represents the short-term memory. What does it consist of? It consists of the input at time step t plus the hidden state h t minus 1 the previous at the previous time step plus the bias. But here we should have assigned the weights for the input. The weights for the input is the W, the matrix W, and the weights for the hidden state is the U here, the learned weights of the hidden state, and this is the bias. And let's have a stop here because we will use this matrix and this matrix in most of these equations to separate or make them disconnect from each other. We add here a sub C and also sub C and also here sub C. But here we want this result, the value from this result, to be squashed into a range between -1 and 1 because we need positive as well as negative data, negative values. How we do this? We use the hyperbolic tangent function, which we can write it here as the tan h and it takes the inputs t, any vector, for example x, and it's very simple that it's x raised to x minus x raised to minus x divided by x raised to x plus x raised to minus x. The result now is, if this is a vector, its values will be squashed into a range between -1 and 1. That's fine. How to do it? We just make this the input into this hyperbolic tangent function like this. And that's it. This is the candidate data, and it's a linear transformation of the weights and the input at time step t, as well as the hidden states, the weighted hidden state. Well, the next equation to talk about, I think it's better to talk about equation number 4, which talks about the cell state update. The cell state update. We have talked about the candidate data and its the input, weighted input, and also the hidden state. Now let's talk about the cell state. Cell state at number G, cell state, as we have said here, it represents the cell state, which represents the long memory. What does it consist of? It's a combination of the long memory at the previous time step C. This is the long memory at the previous time step t minus 1 plus the new candidate data. C, this is sub D, C tilde here. But here we don't want to take all this information. We don't need all the memory, the long memory. And also we don't need all the new data. We need this part of this new data as well as the old data that makes the prediction the best. How we do it? We need two gates. Some gate to decide which data to maintain from the old memory and which data to allow in the this is the new data. How much, which fraction of this data we should take, which makes the prediction the best. We need forget gate here, a vector at this time step, and it's element wise multiplied with each element here in the cell state, the long memory. We use this symbol which represents the element wise multiplication. If this is a vector, this should be the same dimension, same rows, because here in this case it's one column, same rows, and each element here is multiplied by each element here. The same for the candidate data. We need input gate to decide how much to take from the new data proposed by the candidate data equation. Well, that's it. Okay, now let's talk about the forget gate and the input gate. Forget gate and input gate. It's very simple. We can just imagine it as the same mathematics symbol here of linear combination. We need the weighted inputs and the weighted hidden state and also the bias. The bias is some information that we cannot explain. We don't know which variables are here and how much is the weight or the effect of each variable that affects the dependent variable. The forget gate f sub t is the same as we hear. It's the weights, it's t weighted by the weights, learned weights memory, and also the hidden state at the previous time step, as well as the bias. Here. It's here. And also let's add sub, because as we have said, we have repeated matrices of weights. Let's give it the sub f, and also here the weights for the h. We have agreed that it's this u. U is the matrix of weight of matrix of weights for the hidden state. And we give it the sub f, and the same for the bias, because we have different bias. Okay, f decides how much to retain from the long memory. It's a vector or a matrix, and each and before we took it, this should be squashed. The value of this forget gate should be squashed between 0 and 1 because we need fractions here. We need fractions here. How to do it? We use in this case the sigmoid function. Sigmoid function takes input x or whatever variable, nomination doesn't matter here, and it squashes the values of this input to be between 0 and 1, to be a fraction. How to do it? It's very simple. We give it usually the symbol sigma, and this function takes as input x and this squashes it into values between 0 and 1. And this is the equation. 1 over 1 plus e, the Euler number raised to minus x. And x here is a vector. You can see it here, yes. Okay. The input gate is the same math structure like this. So it's I sub t, and also here, of course, we have said we use the sigma, which is the activation function, the sigmoid function. We do the same here. We use the same sigmoid function to squash the input into a range between 0 and 1, and it's the weights, it's the inputs plus the heading state p minus 1 plus bias, and it's the weighted inputs w, the weighted heading state u, and also we give the sub I to make it distinct from different weights matrices. I, also I here, also I here. Until now, so good. We started by the candidate data, the new data, and we also have the cell state data, which represents the hidden state. Now we need the hidden state. Hidden state. This is equation number 6. The hidden state, as we have said here, the hidden state is a filtered version of the cell state. It represents the short memory at time step t. It's a gated nonlinear projection of the memory into the output space. How the mathematics of it? Hidden state. It's the output. The output is here. Let's write it, but let's wait to write it before here. We have said it's a filtered version of the hidden state here into the space of the output, and hidden state should be between -1 and 1, so we use here the hyperbolic tangent function. It's this is the hidden state. Sorry, I mean this is the CT, the cell state. The hidden state is a filtered version of the long memory, hidden state is the short memory. It's a filtered version. It's a filtered version of the long memory C state into the space of the output. And we here to do this we need element-wise multiplication. This is 10 TANH. Okay, so far so good. We have the hidden state. We have the cell state. Now the final step should be the output, and the output is the same idea as the same structure as we have used for the other three equations. So the output is, we use also the sigmoid, and it's the input at the current time step and the hidden state ht minus 1 and the bias. And we add the weights. Weights for the input is W, weights for the hidden state is U, and bias. We add also here O, sub O to make it distinct, and also O here, and also O here. So we have weights for the input. For the forget gate, we have weights for the input gate, for the candidate data, and for the output gate. Output gate. That's it. Now let's make a quick revision about what we have said. Our issue is that we have a vector of inverse x. And for this vector we have different time steps. It starts from t minus 1, the first time step, until the last time step, capital T. And each element can be vector, or in some cases it can be just some single value, such as a time series for inflation values, for example. And we need to use this data because artificial neural network is a data-driven statistical learning approach, a machine learning approach. We use this data to train our model to know the relationships between the different values and different variables, and afterwards we can expect the next time step. Usually we divide the vector into 80% data to train our model, and also we use this data to validate or to test the statistical learning model on the remaining 20%. That's it. We make a looping. In each time we take one time step to update the system and the weights of inputs and the weights for the hidden state. Let's make a very quick revision. Let's start from equation number 3. It's the new data we take at the current time step. The current time step. As we are looping this system. It has weights, and also we use the hidden state we use the hidden state, and we have weights for the hidden state, and also the error of the estimation of this equation. Then we make update to the long memory. Long memory is the cell state. How to do it? It's a combination between the long memory, the cell state at the previous time step, as well as the new candidate data proposed by equation number 3. So these are the most important equation, as well as the equation number 6, which is the hidden state. The hidden state, as we have said, it's a linear or a filtered version. This is a filtered hidden state. Is a filtered version of the cell state. It represents the short memory, and it's a gated nonlinear projection, of the long memory, the cell state, into the space of the output. The long memory is filtered by the forget gate, and the candidate data is filtered by the input gate. Then, using this information that we have created, we can now predict the output using the data xt and also the weights. This is the basic of simple linear equation. But we have here also the hidden state, which we develop through the different steps of this system. And this is to predict the output, we use directly the hidden state. The output here depends directly on the hidden state, and the hidden state, as we have said, is non-linear transformation of the long memory cell state into the space of the output. I hope this is clear. The next, this is the feed forward step, and I will see you in the back forward step to complete this system. Thank you so much for your attention.